Here's our final practice with specific heat. Now, this one's got a lot going on. There's a transfer of heat in this problem. I have a 5-gram piece of aluminum that was heated from 25 degrees Celsius to 78 degrees. Then that hot piece of aluminum was added to 100 milliliters of water at 20 degrees Celsius. How much energy is transferred from the hot metal to the cold water? And then I want to predict the final temperature of the water after the hot metal is added. So here's kind of what's going on. Maybe I have a beaker or a cup of some kind, and it's got water. This is initially 100 milliliters of water at 20 degrees Celsius. All right, well, then I have this hot piece of metal. I don't know, here's my hot metal. Hot metal. Well, if I put this hot piece of metal in some cold water, I got to think about the direction of the energy flow. Energy always flows from a warm object to a cooler object. So that hot piece of metal is going to transfer heat to the water. So this kind of makes sense conceptually, right? That if I put a hot piece of metal in some cold water, that the temperature of the water would increase a little bit. So eventually we want to know, like, well, what would be the final temperature of the water? Will it go up a couple degrees? I don't know. So we're going to start with this first part. How much energy is transferred from the hot metal to the cold water? Well, for that, we need our equation. Delta H equals mass times temperature change times specific heat. All right, well, let's plug in what we know. So this is going to be technically, I'm going to call this energy of the hot metal. Let's calculate the energy of that hot piece of metal. All right, well, we got the mass. We've got a 5-gram piece of metal. We got the temperature change. It's going from 25 degrees to 78 degrees. So I'm increasing in temperature by 53 degrees Celsius. It's temperature final minus initial. Final minus initial. And then specific heat. Now, if I know this is aluminum, I can just look up the specific heat on this table. Here it is, aluminum, 0.902. That's a constant. You'd always be given the chart. 0.902 joules per gram degrees Celsius. All right, so this isn't so bad so far. So we plug it in. 5 times 53 times 0.902. All right, so I'm looking at about 239 joules of heat. That's the energy of the hot piece of metal. But now, assuming no errors, and one of the errors that we'll have to deal with in the lab is maybe energy lost to the surroundings. We want all that heat from the hot metal, the 239 joules, we want all of that heat to transfer into the water. Now, could some of the heat also transfer to the glass beaker? Could it also transfer to the air? Of course. And when we think about system and surroundings, the system is that hot piece of aluminum. The surroundings is everything surrounding it, which I mean the number one particle that's in contact with that hot piece of metal is the water. But some of the heat could be released from the surface of the water to the air. Maybe some of it is absorbed by the beaker. So for purposes of doing this calculation, we're going to make an assumption that the 239 joules from that hot piece of metal is totally transferred to the cold water. Oh, this is the answer to the first part. How much energy is transferred from the hot metal to the cold water? We're going to assume all of it. All of the energy from the hot piece of metal is going to transfer to the water. Okay, I can do that. Well, now the second part of this is to predict the final temperature of the water. Well, for that, we're going to do one more calculation. So this will be in reference to the water. Energy absorbed by the water. So that 239 joules is going to transfer from the metal to the water. Okay, I kind of like this. So we can start with that as our delta H. Assuming that all of the energy is absorbed by the water, delta H is 239 joules. A transfer of energy. Technically, it's going to be exothermic for the metal. The metal is going to lose that energy, and it'll be endothermic for the water, absorbed by the water. Now we'll plug in what we know for the water. Mass. Well, I have 100 milliliters, but you might remember that for water, the density is 1 gram per milliliter. So if I have 100 milliliters of water, it weighs 100 grams. The temperature change, again, I think that's what I'm going to leave as my variable. I know the initial temperature is 20 degrees. I'm going to add this hot piece of metal. I'm going to assume that the water temperature will increase a little bit, but I'll leave that temperature change as my variable. And then the last thing I need is the specific heat of water. So we go back to our table, and we're going to use this first one, the 4.184 joules per gram degrees Celsius. All right, 4.184 joules per gram degrees Celsius. And all we got to do is solve for our temperature change. So we do a little algebra. 239 divided by 100 divided by the 4.184. And we got it. Oh, let's see. My temperature change will be 0.57 degrees. It's small, isn't it? Which will be kind of interesting. So now if I want to calculate the final temperature, I have a few options. So I could use that equation, delta T equals temperature final minus initial. So I could plug this in as my change in temperature. I'm looking for the final, and I know the initial was 20 degrees. So algebraically, I could solve for final temperature, and it really should be about 20.57 degrees. Or you could just use your noggin. Again, if we're adding this hot piece of metal to the cold water, I would expect the temperature of the water to go up. So when I see a temperature change of 57 degrees, it should increase by 0.57 degrees. So we got it. We got our final temperature. Now, I want to look at one thing that's really interesting. So we had the same quantity of heat. It was released from the metal and absorbed by the water. That amount of heat caused a 53-degree temperature change for the metal. That same amount of heat caused about a half-a-degree temperature change for the water. That's interesting, isn't it? Same quantity of heat. Same quantity of heat, but yet the temperature change was not at all the same. 53-degree temperature change for the metal and only a 0.57-degree change for the water. Well, there's kind of two reasons for that. Number one, specific heat. Look at the specific heat of water. It's like 4 times larger than that of the aluminum metal. And specific heat is defined as the amount of heat energy it would take to raise 1 gram up 1 degree. It just takes more heat energy to raise 1 gram of water up 1 degree Celsius. It takes 4 times as much heat energy to increase the temperature of the water compared to that of the metal. That's why if you're ever like walking around on a sunny day and you feel like the metal outside of a swimming pool, the metal could be really warm. You jump in the pool and the water is still kind of cool. But water just has a very high heat capacity. It takes a lot of energy to increase the temperature of water. Now, part of that is because of his strong intermolecular forces. Remember those hydrogen bonds? Water is a very polar molecule, and there's really strong attractive forces in between the water molecules. So it takes a lot of energy to start making them wiggle around faster. When I increase the temperature, all I'm doing is making the water molecules move faster. So there's reason number one. Water has a much higher specific heat. Reason number two, mass. So when I have a transfer of heat energy, that heat is evenly distributed to all particles in the sample. All particles get an equal share of that heat energy. Well, with the aluminum sample, I only had 5 grams. Now, if I wanted, I could turn it into moles, but I guarantee it would be pretty small. So yeah, there's definitely a good amount of aluminum atoms present in the sample. But look at the mass of the water. 100-gram sample. There's just going to be a lot more molecules in this 100-gram sample of water compared to a 5-gram sample of the metal. So if that heat, that 239 joules of heat, has to get evenly distributed amongst all the particles, well, with the water, there's just going to be less heat for each water molecule. And so the temperature is just not going to increase all that much. A little bit of heat has to be transferred to all the particles. That's why I can put an ice cube in a cup of water. And pretty quickly that small sample of water will start to cool down. I put an ice cube in like a giant bathtub of water and I really don't notice much of a change. The temperature will depend on not only the specific heat, but also the amount of particles in the sample. As I have more particles in the sample and that heat gets evenly distributed amongst all the particles, I'm just not going to see as high of a temperature change.